Hello, and welcome to this week's edition of the Taurus Report with Joe Bacos. This week we are going to take a look at cosmic magnetic fields and how CGC can explain these. But before getting into that, I want to explain once again very briefly the central thesis of how CGC presents the gravitational force as a relic of the electromagnetic force. Because a little bit of an understanding, a grasp of that idea and how that works is necessary in order to understand how magnetic fields on a cosmic scale can be generated easily in CGC, even if the cosmos is electrically neutral overall, without a significant movement of charge. Because normally with magnetic fields, well, always with a magnetic field, you must have some sort of motion of charge for the field to exist. If there is no motion of charge, then the field should not exist. And not only that, but even if you have motion of charge, if those motions are all totally randomized, where in every direction the motion is approximately equal, like you have the same number of negative charges heading in this direction as you do positive charges heading in that direction, well, their fields would cancel out. And if you overall randomly have approximately the same numbers of charges at the same numbers of speeds, both positive and negative at all random directions, then overall you should not have a magnetic field, although you might have localized fields here and there, as we always observe. But let me present once again, the basic idea behind CGC. So, what I claim is that inside the nuclei of atoms, the subatomic particles, the proton and the neutron, they are composed of quarks, and quarks have charge, some negative, some positive. And the quarks move at very high velocity, and since they are constrained by the nucleus, so they move at high velocity, and they are constrained by the nucleus of the atom, and so they're like bouncing back and forth. Like if this is the nucleus of the atom, the quarks would be bouncing back and forth all over inside the atom, shifting position. And so one might describe that motion of charge as electric current, because all motion of charge is electric current. However, like I said, because we would assume that it would have no directional component to it in the sense of some sort of polarity. In other words, it's randomized going all different directions. And so there should be not really any detectable electric current or electromagnetism, because all of the various random motions would sort of cancel each other out. So let's take a little bit closer look at this from the standpoint of electrical current in two parallel wires. And this is from Georgia State University, a good diagram. And this is like a classic diagram that, if you first start studying electricity, you learn about this effect. If you have current in two parallel wires, and normally current is electrons like in copper wires, although it could be, theoretically, you could have positive charges moving, but in practice, it's almost always electrons we're talking about. But if you have charges moving in parallel wires in the same direction, those two wires are attracted to each other their magnetic fields, because when you have motion of charge, that creates a magnetic field. So if you have a pattern here where two parallel wires, the flow of electricity is in the same direction, and those two wires are parallel to each other, they are going to experience an attractive force. Now, normally, when this subject is presented, it is, at least I have not seen it presented in the context of alternating current. Now, the wires in our homes, most homes, are alternating current. When you plug a plug into the wall, it's alternating current, and that means that it isn't continuously flowing in one direction, right? The current, first it flows this way, then it reverses and flows the other way, then it reverses again and flows this way, then it reverses, and so it keeps going. So you get this back and forth current flow. Now, if both wires are experiencing that back and forth current flow, then when they are in phase, meaning where they're both going in the same direction, the wires will still feel an attractive force, even though the current's going back and forth. If they're in phase, and all in phase means is that the waveform lines up with each other. So, for instance, and I'm going to go to a Desmos graphing calculator, and I'll include the links. Okay, so if I have, let's say, some current, which we can think of as a sine wave. If it's an alternating current, I mean. So let's suppose we have some alternating current here. Okay, so here's this sine wave. So in this region, let's say when it's positive, it's flowing to the right. When it's negative, it's flowing to the left. So if you have an alternating current, this sine wave would be flowing to the right, and then down here it'd be flowing to the left. And so if you have two wires that you're talking about near each other, let's say I do another sine wave. Let's suppose you have two wires near each other. Okay, so here's two wires near each other. Now, if they are in phase, where they're both positive in the same region, then you will have an attractive force between those wires. You will have an attractive force. Now, if they are anti-phase, so let's suppose I do one of these okay, let's suppose they're anti-phase like this. If they're anti-phase, where one is negative when the other is positive, then these two wires are going to be feeling a repulsive force away from each other. And so with alternating currents in two parallel wires, we can show that, let's see, there's 2 points I want to make about this. So first, if we introduce parallel wires that have alternating currents in them, and the new and unusual thing is to experiment with this with alternating currents. If there are alternating currents, then they can experience both attractive and also repulsive forces, because if the current is flowing in the opposite direction, they will repulse each other, whereas if they're flowing in the same direction, they will attract each other. So getting back to what I was talking about, what does this have to do? What does this have to do with the nuclei of atoms and gravity and all of that? So as I said, we can think of the quarks reverberating around the nucleus as an electric current, and probably all it would take for this to generate the gravitational force as a form of magnetism, all it would take is 1 part in trillions, just 1 part in trillions, to be approximately in phase and approximately spatially aligned to fully account for the gravitational force. And so what I'm claiming is that all matter has these sort of vibrations or fluctuations going on in the nucleus. And so some super tiny portion of them happen to be somewhat aligned and somewhat in phase. And that is what accounts for the gravitational force, because the electromagnetic force is trillions upon trillions upon trillions of times stronger than the gravitational force. So all it would take is just some small quantity of these things to be in phase and lined up in that way. And so I present this in my paper, and once again, if you go to browser and you just type in torusreport.com, all as one word, torusreport.com, and hit enter, then that will bring you to my website. And then if you go down here and click on the paper CGC, it will bring you to this paper, where you can see in the first sections of the paper I explain all that very carefully. So this is like a schematic sort of where this is the sun or the earth or any other large body. And within the nuclei of each atom, you have back and forth motions going on all the time. And so what I am saying is, among all of those motions going on, all it would take is 1 part in trillions to be somewhat aligned and somewhat in phase for them to fully account for the gravitational force. And so, and you also, you can have a repulsive gravitational force. And in my opinion, that is what accounts for the fact that most of the galaxy clusters and superclusters are accelerating away from each other, is because they are actually just experiencing a repulsive gravitational force. And it is not that space itself is stretching. It is that they are actually, most of them, accelerating away from each other, because our universe is in a phase of expansion, but at some point it will enter into a phase of contraction. So let's take a look at this, at waveforms like this, to try to understand what's going on with gravity and why it can explain the cosmic magnetic fields that we are detecting. So if we again go to Desmos, and let's turn on this waveform. So first, if I do this, and I just have a wave, let's suppose I just have a wave. And let's suppose it's just sine x. Okay, a few problems with this. Let's suppose this was the gravitational force. Okay, there's a few problems here. So first, we know that the gravitational force decreases with distance, right? And that is why we must divide by the distance. So let's suppose the horizontal axis here is distance. Okay. And so if I divide by distance, then we can see that now the force is decreasing with distance. Okay, the force is decreasing with distance. Now, we also notice that if what I'm saying is correct, and at cosmological distances, like between galaxies, it is repulsive for huge spans of distance. We know that the force must be repulsive. That means that there must be a kind of a phase stretch, which I accomplish in my models by doing this. Okay, and so I have a sort of a phase stretch. And so you can see that with this model, over time, the areas of, so anything above the line, here is where gravity is attractive. And then anything below the line, this is where gravity would be repulsive or pushing away. And so we could see that over time, the phase gets stretched. And what I'm claiming is that most galaxy clusters would be in a phase distance away from each other where it is repulsive gravity below the line and they are all pushing on each other. But at some point, when they get to the right distance, then gravity will turn attractive again. And so then all of the galaxies will begin moving closer together again. And so, according to CGC, the universe is eternal, and it goes forever alternating between these phases of gentle expansion and contraction. And there is no such thing as a Big Bang or Big Crunch or anything like that. Instead, the universe is just eternal and gently alternating periods of expansion and contraction. Now, one of the things it means to approach gravity in this way is that gravity is much more complicated than the way that it is presented in standard Newtonian or general relativity theories of gravity like that. I am saying that there is not a simple and elegant force law. It is true that one aspect that all the theories have in common, of course, is that it decreases with distance. The force decreases with distance because it is based on the electromagnetic force. And so, of course, you do have this sort of general trend. However, because I believe it is phasic, I think that it alternates areas of very strong gravity and areas of weaker than expected gravity, and sometimes even repulsive. And all of this depends on systems which themselves are like rotating and cycling, whether you're talking about a solar system or a galaxy cluster or a supercluster or great walls that we find, the way that the universe has this sort of sponge-like distribution of mass throughout it. It means that gravity and the way it works is much more complicated than standard theory is thinking. And so you end up with having to make a lot of adjustments. And I kind of like to show you what I mean is, let's suppose we're looking at a basic equation like this red line here. And let's suppose that's the behavior of galaxies at the distance of, I don't know, a galactic cluster or something. Okay, well, there are motions within each particular galaxy, right, that might adjust things and cause things to change a little bit. So if I take a factor and let's say I add that is itself cyclical, right? Then I end up with something that is, quite a bit different here. Let's see. Let's go with that. Yeah, there we go. Something like that. Okay, so let's suppose I add to the gravity caused by the clusters. I add a factor to account for the rotation of the galaxy. And then within the galaxy, you have all these stars in motion and everything else. And things get very complicated very quickly. You get waves within waves, and trying to decipher all this and put it into a simple and elegant force law, I think would be impossible. I think instead that what we need to do is instead do something which I'm often criticized about, which is just like plot points showing, how objects are moving. Whether you're talking about galactic rotation rates or you're talking about galaxy clusters accelerating away from each other, whatever you're talking about these macro movements, just assume that that is the way gravity is operating in that context at that distance, and then make a kind of a patchwork force law for that context, just based on plotting points, and you just say, okay, this is how it's behaving at these distances and in this context. Then for galactic rotation, you might have another force law and just say this is how it seems to be behaving in this context. For the formation of solar systems and formation of planets, you might have something else. For well-established systems that have been stable for a long time, there's a process that I call acclimation, where I believe that galaxies, that masses tend to settle in circular orbits that sort of respect Newtonian type law, and it looks much like that, like in our solar system, for example. And so I believe in a sort of a kind of a patchwork amalgam of force laws for gravity, that we kind of all patch it together, like sort of in a rough ad hoc kind of way, and just don't claim to have a simple, elegant law. Now, so how does all this, the thesis of tonight's topic, I haven't even talked about that yet after all this time. I was sort of laying the groundwork in order to, so that the viewer might have an idea of where CGC is saying that the force of gravity is coming from, so that it seems more understandable or believable when I explain why I think that CGC has no problem at all explaining cosmic magnetic fields. So if we take a look at online, for instance, let's take a look at like this recent article on this. Over at MIT, they have done some research trying to explain, because it's a pretty big mystery. We've detected these cosmic magnetic fields, and I'm calling them cosmic because the field lines are going over vast distances, between galaxies and galaxy clusters and everything else. And when you have magnetic field lines, going across such huge distances, then you naturally start thinking, well, do we have charges moving in such an organized way for all of these distances? You immediately start looking for something like this. You have a flow of charge, right? And a flow of charge creates sort of an organized magnetic field, right? And so, in my opinion, everyone has been sort of assuming, this sort of one-directional flow of charge, whereas I am saying that in CGC, you can have vast systems that are totally charge neutral, yet within them there may be back and forth motions that, when they are synchronized and when they are in phase, then you'll get magnetic fields. And so it makes perfect sense in CGC that you might detect weak magnetic fields, spanning the entire cosmos, as these do. And in CGC, it makes sense that you have this kind of thing, just because of the very nature of what the gravitational force is. Now, these particular researchers at MIT, they are trying to develop models to sort of explain how this cosmic magnetic field could have possibly developed from the time of the Big Bang. And so they are trying to show how the original field might be seeded to start with by various flows of charge at the very beginning of the universe, and then try to show how that might develop through modeling to the time now where we can see the existence of these fields in the present. Now, in that sense, I'm a fan of modeling, of course, but the difficulty I have here is that recent web results, as you know, because I've done several shows on this, recent web results are showing, in my opinion, that there was no Big Bang. And so I think that approaching cosmic magnetism from that standpoint isn't going to work out. And instead, I think that these cosmic magnetic fields show that there's a fundamentally difficult thing to explain here unless we move in the direction of presenting the force of gravity as intimately connected with what we're seeing. And so that's sort of a roundabout way of my saying that I think the force of gravity is an expression of the electromagnetic force. And so, in other words, at rock bottom, it is not a distinct force from electromagnetism. And so, in some sense, that means that I support a sort of electric universe view of things. Now, what this means is that, in my opinion, to detect some of what I'm talking about, the best technology, the best hope for like directly observing what I'm talking about, which is these charge fluctuations within the nuclei of atoms, such that, where what we're observing is charge neutral in the sense, obviously a nucleus is positively charged, but what I mean by charge neutral is that we're not seeing a polar separation of charge within things like protons or neutrons. And I am claiming it's because the quarks are moving at such high velocity back and forth that we don't see this polarity. But this back and forth motion is an alternating current, and as I've explained in this episode, if the currents are in phase, you get a magnetic field. So my point is, in bringing that up again, is that the best technology that might have a chance of seeing this would be nuclear magnetic resonance imaging, NMR. And most of you have probably seen some of this technology at some doctor's visit or a visit to the hospital where they can look inside a person and see details. And that is based on magnetic moments within the nuclei of atoms. Now, the problem is that is looking at the subatomic particle level, so at the level of protons and neutrons. So it's kind of looking at that level. Well, to see what I'm talking about, which is cyclic motions of quarks, that equipment would have to be something like 1,000 to 10,000 times more sensitive than current tech. And so, but still, with all that said, that is the best hope to have observational confirmation of what I am saying is tech that develops from that type of technology, NMR technology. Now, next week in the Taurus Report, what I'd like to do is to do a summary of all of the things that we have seen from Webb recently that sort of confirm what I have been saying, that Big Bang cosmology, in my opinion, just does not make any sense anymore based on what we're seeing. And further than that, I think this is obvious. I think it's very obvious. And so I would like to summarize all of the items that we're seeing and sort of give a CGC response to those items and why CGC is very consistent with what we're seeing. But in any case, I want to thank you once again for tuning in. Have a wonderful week. And we will see you again next week. Bye bye for now.